Hey everybody, welcome back. This is lesson 4 in unit 6, and today's lesson is called the combined gas law. So in the last video, we talked about Gay-Lussac's law, and he talked about the relationship between temperature and pressure. And so this was a direct relationship, which meant if temperature went up, pressure went up, or oppositely speaking, if temperature went down, pressure went down. So again, in a direct relationship, things do the same. Both variables do the same thing. Okay, so again, today we're going to combine all of the gas laws into one to form the combined gas law. So just a quick recap of the three laws that we've gone over. Boyle's law talks about pressure and volume. Here's the formula. It's an inverse relationship, so that means if one thing goes up, the other thing goes down. And it looks like that kind of curve down. Then if we look at Charles' law, that talks about volume and temperature. So here is that formula. And this is a direct relationship. So again, like we said before, one goes up and the other goes up. So they do the same thing. And you can see that by that, straight line pointing up. And then lastly, we have Gay-Lussac's law, and that looks at the relationship between pressure and temperature. Again, here's that formula, and it has a direct relationship and has that straight line going forward. So something to kind of point out, maybe you've noticed this. Charles' law and Gay-Lussac's law have very similar looking formulas. They're both direct relationships. And then Boyle's law is kind of that black sheep. It kind of just doesn't totally match up with everything. So those are the three laws. So we've practiced them individually, but good news, first of all, you don't need to memorize it. Second of all, we can combine all of them into the combined gas law. So take a second, think about what that might look like. So if you've thought about it and tried to combine all three of these formulas, the combined gas law looks like this. So this is on the back of your reference table, so you don't need to memorize it. But let's look at it. Here in blue, hey look, that's Boyle's law. If we look at the green, doing P, that is pressure and temperature is Gay-Lussac. And then if we look at the other one, volume and temperature, that is Charles' law. So all three of these formulas are right here in that one thing. So that is the combined gas. So that's how everything would combine to form each other. And so this is why you don't need to memorize them specifically, because it's literally all there. So again, the combined gas law combines all three of these laws. Just like always, temperature still needs to be in Kelvin. So remember, Kelvin equals the degrees Celsius plus 273, and that comes straight off the reference table, just like that. It's the very last formula on the back of the reference table. STP still means something, so there you have to check table A. It has two possibilities for standard pressure, 1 atm or 1.3 kPa, and it also has two options for standard temperature, but again, we need to use Kelvin, so we only really care about one of them. Now, other kind of things to think about when we are looking at the combined gas law, equation, different questions with it. Sometimes the whole formula may not be needed. So we'll go over an example like this. If a variable is not mentioned in the question, or if it says, hey, this variable is held constant, then we can just kind of ignore it to make our life a little bit easier. Again, we'll go through an example like that. So with this, and like always, but especially now because it looks a little bit more complicated, it is super, super, super important. You take your time, you stay organized, you write down all of your steps. So let's get into it. We have this question. A 220 ml sample of helium gas is in a cylinder with a movable piston at 105 kPa and 275 K. The piston is pushed until the sample has a volume of 95 milliliters. The new temperature of the gas is 310 K. What is the new pressure of the sample? So here is a pretty basic combined gas law question. So again, your first step would be to write down your knowns and unknowns. So now we're going to have all three of them. So looking at this, 220 mils, that is going to be our volume 1, 220 mils. With a movable piston at 105 kPa, that is our pressure. And 275 K, so that is our T1. So now we got to look at the, this should be P2, the final conditions. Again, we have this before and after situation. So piston is pushed to 95 mils, 95, so that's our volume 2. The new temperature is 310, and we're looking for that. So now all of your variables have been pulled from the question, and we're ready to get started. So here we have all the variables. Now we have 5 of them. We have to solve for that 6th. So if we plug stuff in, you get 105 times 220 over 275 equals P2 times 95 over 310. So again, we just plugged in all of the numbers as is. So I'm going to bring this up here. If we try to simplify it a little bit, you get 23100. So that's 105 times 220. Again, we're going to put that over 275 equals P2 times 95 over 310. And so now we're going to cross multiply. So you get that. So again, if we're writing every single step out, that looks like this. So 23100 times 310 equals 275 times 95 times P2. So that is our cross multiplication. And so if we do some math, 23100 times 310 is this, 7161000. And then 275 times 95 gives you 26125 times P2. So now I want to get P2 by itself. 26125 divided by 26125. And your final answer is 274 kPa. And that is your P2. And so just to point out, we know our unit is going to be in kPa because first we're looking for pressure, but our starting pressure unit is kPa, so our ending pressure unit will be kPa. And there you go. Okay, so going into the next question, we have our formula. So let's write P1, V1, T1, P2, V2, T2. A cylinder with a movable piston contains a gas having a volume of 6 liters. 6 liters at 293 K and 1 atmosphere. And then, what is the volume? So we're looking for this. When the gas is heated to 303 K and the pressure is held at 1 atm. So in this case, this is why it's important to write all of your stuff down. Pressure is held constant. So if pressure is held constant, that literally is, we go back, Charles' law. So if pressure stays the same, we don't need it. So I mean, you totally can throw it into your equation, but since it stays the same, it's not going to affect our problem at all. We can just get rid of it and use that formula. So if we plug, let me grab a different color, all of that in, 6 liters over 293 equals V2 over 303. We do this cross multiplication, and 6 times 303 gives you, well, first we have 6 times 303 equals 293 times V2. And so 6 times 303 is 1818, and 293 times V2 is 293 times V2. Again, to get V2 by itself, divide both sides by 293. and then out pops the number 6.2 liters. And again, we know the answer is liters because our starting volume unit is liters, so our ending volume unit should be liters. And there we go. Now, if you're somebody who doesn't like crossing stuff out in your equation, you could have done, left P1 and P2 there and plugged in 1 times 6.0, gives you that, equals 1 times V2, 303. Now, you could have solved for that exactly the same. You will get the same exact answer. So again, if something is held constant, and it says it's held constant, or it's not even mentioned in the question, you can ignore it from your formula. Okay, so let's do one last question together. Here we have, again, P1, V1, T1, P2, V2, T2. Okay, a sample of gas occupies a volume of 50 milliliters. 50 mils is going to be our V1. In a cylinder with a movable piston, the pressure of the sample is 0.9 atmosphere, so 0.9 atm. The temperature is 298 K. What is the volume of the sample at STP? So we're looking for that. Now here you might be, we're missing literally all of our, second column, those P2 and the T2. And you're probably like, what am I supposed to do? I can't do this. You can. Remember, not that. STP means something. So standard temperature and pressure, we got to go to table A. So standard temperature is 273 K. It's also 0 degrees Celsius, but remember, we have to use Kelvin. And then for our pressure options, we have 101.3 kPa, and we have 1 atm. Now for this question, which one should we use? We have to use 1 atm because if we're starting an ATM, we have to end an ATM. We can't just create new units because we feel like it. Plus, this is also the easier number to use. So now we have 5 out of the 6 variables. We are able to solve for that fifth one. So again, if you're ever not given a a variable or a number in the equation, chances are the letters STP are there. Okay, so with that being said, we have 0.9 times 50.0 over 298 equals, so that's the first half of the equation, times 1.0 times V2 over 273. So right there, all we did was plug in our variables. And then simplify some stuff. 0.9 times 50 is 45 over 298 equals 1 times V2 over 273. Again, we're going to cross multiply. And so you get 45 times 273 equals 298 times 1 times V2. So if we simplify that a little bit, 12285 equals 298 times V2. So now we want to get V2 by itself. Divide both sides by 298. That magically goes away. And then we are left with 41.2. And that is V2. And our unit should be milliliters. So again, we're starting in milliliters for volume. We should end in milliliters. Again, you need to stay consistent with your units across the board. The only time you'll ever change a unit is if you're given Celsius and you have to convert to Kelvin. That's it. So that's it for all the gas law equations and math. Next episode, we'll talk about real versus ideal gases and the kinetic molecular theory. So that's more conceptual stuff. For now, we're done with learning new calculations. Hopefully you found that